In 1801, Gauss wrote the following: if a number n measures difference between two numbers a and b, then a and b are said to be congruent with respect to n. Let m be a positive integer. We say that two integers a and b are congruent modulo m if a minus b is a multiple of m. In other words, m divides the difference a minus b, and we write that a is congruent to b mod m. Here's an example. 32 minus 17 is 15 times 3 times 5. Right? It's 15, which is 3 times 5. So 32 is 17 mod 5. 38 is 17 modulo 7, since 38 minus 17 is 21, which is 3 times 7. Now note that 38 and 17 both have a remainder of 3 after divided by 7. Now this leads us to the following proposition. Two integers a and b are congruent modulo m if and only if they have the same remainder after division by m. Here's the proof. Suppose that a is equal to qm plus r1 and b is equal to pm plus r2. So we essentially perform Euclid's algorithm on ab. Here, then we may assume that r1 is greater or equal to r2. So that tells us that r1 minus r2 is less than m, and that's a positive number. Now assume that a and b have the same remainder after dividing by m. Then a minus b will be equal to the quantity written on the screen, and because r1 minus r2 is 0, then a minus b is divisible by m, and we'll say that a is congruent to b modulo m. Now for the converse, let us suppose that a is congruent to b modulo m. That is, a minus b is divisible by m. Now we obtain that r1 minus r2 is also divisible by m. Check the work on the screen, and since r1 minus r2 is sitting between 0 and m, we get the desired result. Here are some fundamental results. Given a, b, c, d, and k, which are integers, and m is a strictly positive integer, if a is congruent to b modulo m, then ka is congruent to kb modulo m. If a is congruent to b modulo m and c is congruent to d modulo m, then a plus c is going to be congruent to b plus d modulo m. Thirdly, if a is congruent to b modulo m and c is congruent to d modulo m, then ac is congruent to bd modulo m. Finally, if a is congruent to b modulo m, then a power n will be congruent to b power n modulo m for any natural number n, for any integer n. Let's prove the third result. Assume a is congruent to b modulo m and c is congruent to d modulo m, and write a as follows. A is b plus pm, p1m, and c is d plus p2m for p1 and p2 integers. Then a times c will be the product on the screen. Foiling all of this out with some simple algebra, and then factoring m out of the last group, give us that AC is congruent to BD modulo M. Here is an example. Take 93 power 25 modulo 7, and we'll evaluate this without working too hard. Well, 93 is 2 modulo 7. Thus 93 power 25 is congruent to 2 power 25 modulo 7. Now 2 cubed is congruent to 1 mod 7. And then applying part 4 of the previous results, we get automatically that 2 power 25 modulo 7 is congruent to 2 modulo 7. Therefore, 93 power 25 is congruent to 2 modulo 7. Now let Zm be the set of all numbers in between 0 and m minus 1, and define x plus y, where plus here is a new operation, as x added to y in the usual sense modulo m, and x times y is really x times y modulo m. Here is x multiplied by y in the usual sense modulo m. These operations are all well defined, and indeed one can check that x plus y is the remainder obtained after adding x to y in the usual sense and then modding out by m, right? And such an element, whatever it is necessarily in Zm. Similarly, x times y is the integer obtained when we take x multiplied by y in the usual sense and then we mod by m. And whatever number we get is of course going to be an element of Zm. Now, moreover, note that these operations are all commutative and then they're also all associative. So you can prove that. Try it at home. And finally, Zn when endowed with addition modulo n is actually a group. In fact, it's a commutative group.